Hello and welcome to this webinar. I am José Ignacio Barbero from Tecnalia and will be the chairman of this session. I work in Tecnalia, a research center in Spain, as project manager for the steel industry, and I have a master's degree on mechanical engineering. We develop projects to improve efficiency and productivity of steel making processes and to improve quality and properties of steel products. The Siderwin project has been supported by the European Union under the Horizon 2020 program and is going to be finished this month. In this webinar, we will try to show you the main results of the project and the lessons learned and some future perspectives. In the agenda of the webinar, this is the agenda of the webinar, but that you already know. But before we start, there are some additional comments. This webinar is being recorded and will be available later for you to, and you can share the link to anybody. You are free to share the link. All the attendees will have the microphone muted and also your cameras, but you can communicate with us through the chat. So you want to send us any comment or question, please write it and we will register everything. And we will try to have some time for questions after each presentation. And if not, at the end, there will be some additional time for questions and answers. So the first presentation is going to be the general overview of the project that is going to be done by Valentin Weber-Zollinger, that is the coordinator of the project. Valentin holds a PhD degree on materials engineering. She then joined ArcelorMittal Global R&D in 2008, where she became a recognized energy specialist with a background on projects related to energy optimization at integrated steelmaking, CO2 emission assessment, etc. After some years of leading a transversal team dedicated to physical chemistry and surface process engineering, she took the lead of the carbon neutral breakthrough processes team, which focuses on the development of the iron electrowinning technology. Since last June, she became the coordinator of the Siderwin European project. Valentin?
Thank you, Jose, for the introduction. Can you hear me well?
Yes, but we cannot see you.
My camera is activated.
Yeah.
And my colleague is able to see me. Yeah. Is it working right now?
Yeah. Yes,
okay.
It's okay.
Thank you very much for the introduction. So, good morning, good afternoon, everybody. And thank you for coming. I have the pleasure and the honor to introduce this webinar talking about the Siderwin project, and I will give you a brief overview of the project. Next, please. Yes. Okay. So objectives of the Siderwin project was to develop an innovative electrochemical process to transform iron oxides into steel metal plates, and producing steel by electrolysis, of course, without direct CO2 emissions. And the objective of this project was to define a completely breakthrough route compared to conventional steelmaking routes. As you can see here on the left, you have the conventional, what we call the traditional blast furnace BOF route, compare on the left with the Siderwin route, and you can see that we will avoid a lot of processes for the production of steelmaking, and of course, by doing the direct electrification of the production, we will avoid a lot of CO2 emissions. And this will be done through electrowinning at low temperature in an aqueous electrolyte. So we defined at the beginning of the project, and we have worked on 5 different objectives. So the first one was the development of an electrochemical route for primary steel production. So completely a breakthrough compared to traditional route, as I said before, from iron oxide and without fossil or carbon fuels. The second objective was to work on the industrial feasibility of this new route by the erection of a pilot that you can see here on this picture. And as a reminder, we started from, well, the background of this project, we started from a smaller pilot, just to give you an order of magnitude, and we completely upscaled it to have this pilot developed during the project. The third objective was related to raw material efficiency during steel production, because indeed we are working on the possibility to use alternative raw materials coming from residues from other industries in order to, well, to support the circular economy. The fourth objective was related to the compatibility with the renewable energy sources. And for that, we worked on the possibility to, and on the flexibility of the electrowinning process, and by using the pilot to validate the fact that we will be able to interrupt easily the process, thus matching with the requirements for the deployment of the renewable energy sources. And the last objective was, of course, to be closer as possible to market research and to study the profitability of this new business model and this completely new route. So Siderwin project has started in 2017 and will be ended at the end of this month. So it was a 5-year project. The total budget of the project was 6.8 million euros, with a major part for the pilot erection. We were 12 partners for different companies, for a small and medium enterprise, for research and technological organization, from 7 different countries, and of course it was a multi-sectoral work. We had, of course, steel makers, non-ferrous company, and also power company, and it was coordinated by ArcelorMittal. And I really would like to thank all the partners and colleagues that were involved who were involved in this project for all the work done, and you will see the very promising results that were produced during the project. And last slide, as already said by José Ignacio, this project has been funded by the European Union through the Horizon 2020 Research and Innovation Program. And we, of course, thank the European Union for their support. Thank you, José Ignacio. I will let you the floor.
Yes, okay, thank you, Valentin. So the next presentation is the decarbonization strategy of ArcelorMittal, and how and why is iron electrowinning a promising of the future of steel, and will be presented, there is a last minute change, by Jean-Paul Aleman. Jean-Paul is an engineer specialized in metallurgy, PhD in material physics, in steel industries such as Solac, Usinor, Arcelor, and ArcelorMittal since 37 years. He started his career in R&D, then in quality department to become head of finishing lines at Florange plant, continuous annealing, metallic coating, and organic coating lines. Since 2004, he was back at the R&D as research center manager, first in Montater Auto Application Lab, and then in Messier Process Lab. Currently, since 2022, he is R&D Process Portfolio Director in charge of strategic initiatives. So, Jean-Paul, go ahead, please.
Thanks. Do you hear me? Thanks a lot, José Ignacio. Hello, everybody. Thanks for your participation to this webinar. So I will present you the decarbonization strategy of ArcelorMittal, how and why electrowinning is a promising innovative technology for the future of steel. So first of all, I would like to say that I will do this presentation on behalf of Pedro Prendes, who has initially planned to do this presentation. Pedro is a portfolio leader of process R&D, but unfortunately, he is busy today in Brazil with some disturbance in his agenda, so he apologizes. He can't be present with us today. So, as you know, steel industry is responsible for around 7% of global CO2 emission, and the steel demand is expected to rise 2.4 around billion ton into 2050. So it's really important to decarbonize our steel production, and ArcelorMittal has adopted an ambitious set of carbon targets, which will lead our enterprise in reaching net zero by 2050. And as you see on this slide, there are different steps. First step is to reduce by 25% the carbon emission by 2030, and especially in Europe, the objective is 35% of reduction in carbon emission to reach at the end the net zero emission by 2050. Next slide, please. So we are here disclosing a roadmap that shows our journey to net zero. So our roadmap is featuring 5 grouping of action and initiatives that act as stepping stones to achieve this carbon neutrality objective by 2050. This 5 group of action are for sure the steelmaking transformation from the classical today BF-BOF route to 3 important routes which are and I will come back on it later. So H2DRI EAF, smart carbon BF, and for sure electrolysis of electrowinning of iron. One important point is the energy transformation. So more and more we will need to meet this net zero objective. We will need more and more electricity, and for sure green electricity. We will need more and more hydrogen. We will need to develop a solution for carbon capture, storage, and use, and a solution for energy storage. Still, objective is to increase the use of the scrap, develop more and more, as mentioned before, the EAF route. So we will need more and more available scrap for our industry. E is a sourcing of a clean electricity to reduce the scope 2 emission. Electricity, as already said, will become a greater part of the energy mix we will use to make steel. And E is offsetting of a residual emission. After all the action already mentioned, there are likely remaining residual emission estimated today up to 5%. So next slide, I will briefly explain what is our roadmap on CO2 reduction. So on this slide, you have the evolution from 2018 to 2030 with expected 25 reduction of CO2 emission. So our plans between 18 and 30 is based on ongoing project plans of proven technologies that we can immediately implement. For incremental saving to investment like natural gas DRI and conventional EAF, it is what we can commit 100%. And to illustrate this point, we can see here on this graph the different still announced project that ArcelorMittal is putting in place, such as the announcements, in Sestao and Riron for implementation of a DRI EAF plant, the implementation outside of Europe in Hamilton of also in DRI and EAF plan to be start in 2028 with the objective of starting in 2025 in Hamburg H2 DRI pilot and also with trials in Contrecoeur, Canada with H2 DRIs, and it also has been. I would like to mention the acquisition in US of Corpus Christi plant, so a DRI installation for more than 2 million ton of DRI. So a lot of still announced project in ArcelorMittal to reach this 2025 reduction of CO2 emission. After 2030, we will rely on technologies that are being developed while we are speaking, and development also of infrastructures that are needed to be built. And this is exactly where Siderwin and electrowinning process will have a significant role. Next slide, please. So just to briefly explain what are the 3 steelmaking routes towards decarbonization that ArcelorMittal is working on. First is a smart carbon route, what we call today the smart hydrogen BF route. The objective is to reduce drastically the amount of CO2 emission in this, I would say, classical production route using blast furnace by the introduction of hydrogen in the tier, by also solution of carbon capture, CO2 capture at the top gas, and use transformation and use of this carbon as bioethanol. It's a project that has been developed in Ghent plant and start a few months ago to produce bioethanol, together also with a new project also on Ghent plant, the Torero technology, in order to use circular carbon to produce feedstock for biomaterial production. So it is the first route that is today explored by ArcelorMittal to reduce its impact on CO2. The second one, next slide, please, is a DRI-based route. Sorry. The DRI route is today a route which is very well known, using natural gas. So for sure, the first objective will be to deploy DRP plant using natural gas, and more and more transforming this process to full H2 DRI, as I was explaining before, with today some already planned trial in Contrecoeur in Canada, and a pilot plant in Hamburg, to reach this goal of DRI H2, which will allow us to reach carbon neutrality. And for sure, the third route, next slide, please, is a direct electrolysis route with Siderwin iron oxide electrolysis, which is the objective today, to give more information on where we are with this very promising process for the future. Why promising? Because for sure, and it will be shown in the next presentation, it's a process allowing us to reach a net zero CO2 emission. It's a process with a good energy efficiency. We will have some explanation about the last results on the Siderwin pilot with 2.7 megawatt-hour per ton produce of energy consumption, which is a really interesting amount of energy consumption. As Siderwin, it will be also explained, is a cost competitive process compared to other route for steel production. It's a technology with a strong scalability, and which is modular, depending on the number of cell we will use on the production line, and it's a streamlined operation for sure. As you see on this scheme, is a very, within bracket, simple route of production of steel. So this is to briefly explain what is the strategy of ArcelorMittal in terms of decarbonization, and in this route for decarbonization. And I insist, electrolysis, electrowinning is a very important processing route to be developed for us. Thanks a lot for your attention.
Thank you very much, Jean-Paul. There is a question here. Please, you have shown several technologies to achieve the net zero emission by 2050. So how does ArcelorMittal see Siderwin compared to other technologies to achieve this objective?
How ArcelorMittal see this technology out of the other? As I said, we expect a strong development of electrowinning process. It will be presented. I don't want to disclose the last slide, but Valentin will present you in the conclusion what is ArcelorMittal roadmap of development and industrialization of this process. So for sure, we are speaking of development of electrowinning by 2050, but we expect to be ready by very sooner than 250 for first industrialization of this process. I can say that in the coming years we will be able to produce on a line electrowinning iron.
Okay, thank you very much, Jean-Paul. There are some more questions, but we can keep it for the end of the webinar. And now we can continue with the next presentation that is by Daniela Lopez about the iron electrowinning and to show the lesson learned. Well, Daniela is a researcher at the Aveiro Institute of Materials from the University of Aveiro in Portugal and has her PhD degree in advanced material and processing. She has been working within the scope of the Siderwin project since her PhD thesis and also after its conclusion. Her work has been focused on electrochemical reduction of iron oxides and water splitting towards green hydrogen production. So, Daniela, it's up to you.
Thank you, Jose, for the introduction. So I will be focusing on the lessons learned. So next slide, please. So the traditional iron making route is still, until today, mostly used by the blast furnace, where iron ores are carbothermically reduced into metallic iron, releasing CO2. So one alternative can be the electrochemical based route, which can be performed in acidic or alkaline conditions with much lower temperature in comparison with the blast furnace. And as byproducts, we have only hydrogen and oxygen. So it's a CO2-free technology. Also, there is a specific study that reports lower energy consumption. Next slide, please. So it is possible to perform the electrowinning in both alkaline or acidic medium. But what have we learned? That in acidic conditions, there is a redox cycle loop between iron 2+ and iron 3+ species that lowers the Faraday efficiency. Also, we have observed brittle iron deposits and much stronger concurrent hydrogen evolution. So all of these effects can be minimized if we opt to use alkaline conditions. Next slide, please. So what are the general concepts of the electrowinning? So first, we should start to use a strong alkaline electrolyte, such as sodium hydroxide, that can go up to 18 molar solution, and low temperatures that can go until 110 Celsius degrees. Here you can see a basic electrochemical cell made by one working electrode, can be nickel plate, steel rod, where the reduction to iron will occur, and the counter electrode and the reference electrode. During this reduction to iron, we also have some water splitting occurring in the cell. So we have to consider hydrogen evolution on the cathode and oxygen evolution on the counter. However, what we learned is that hydrogen evolution competes with iron for the cathodic current. So it decreases the efficiency during the reduction. Next slide. So there are two approaches for the reduction. The first one is to use powder suspensions, iron oxide suspensions, mixing the electrolyte, and we can use cathodes such as nickel plates, steel rods, and to deposit the iron in the cathode, as you can see here, the metallic iron deposits. Or we can use ore piece of ore, can be iron oxide pellet, for example, and we can attach it to a current collector and use it as a cathode in the electrowinning cell. Next slide, please. And how this works. So hematite cannot be reduced to metallic iron in a single step. So depending if it's a suspension mode or a bulk cathode mode, the reduction occurs in a different way. Generally, iron oxides are not soluble in sodium hydroxide. So that's why we need to increase the concentration of the alkali, and also we need to increase temperature. So when the hematite particles are around the vicinity of cathode in suspension mode, there is a partial dissolution of hematite to iron 3 aqueous species that are going to be further reduced to iron 2 aqueous species and later to metallic iron that is deposited on the cathode. If we consider the bulk cathode mode, we obtain frequently presence of magnetite. So we can say that it's reduction of hematite to magnetite, especially in the side of the current collector. And later it will be promoted to the reduction to metallic iron. Next slide, please. So now I'm going to present you some case studies, what we learned with them. In the case of hematite suspensions, we obtain until now always very high cathodic current efficiencies, over 90%. But for this, we need to use strong alkaline conditions, over than 30 weight percentage of sodium hydroxide, which corresponds more or less to 10 molar of solution, over than 10 molar. And also we have better results if we use over than 70 Celsius degrees. Next slide, please. We also have learned that if we have some current interruptions, we can still have some high efficiencies. For example, in this case, we have performed two types of experiments, one by shutting down completely the current for 8 hours in a row, or periods of 1 hour. And in another case, we will let pass just 10% of residual current in the same conditions. We have learned that with 10% of residual current, we have highest efficiencies, especially in the case of 1 hour of interruptions. There is also to minimize the risks of iron oxidation when we have this 10% of residual current. Next slide, please. We have also learned that by adding magnetite powder into suspensions can be beneficial for the reduction. We also find that magnetite by itself as an oxide suspension can have around 69–70% of efficiency when compared with literature studies that report only 5%. We can consider the introduction of magnetite as a feedstock in a hematite mixture. We also have reported efficiencies all above 65%. So we can use iron ores with high content of magnetite and also consider feedstocks as metallurgical residues rich in magnetite. Next slide, please. We also learned that it's possible to do this electrowinning of iron through bulk cathodes. However, we learned that this is not so feasible in dense pellets because we achieve very low Faraday efficiencies usually. So we need open porosity for the electrolyte to percolate inside of the pellets to have efficiencies over than 80%. So bulk cathodes work, yes, but have limited prospects for industrial processes. So they are more feasible for studying the mechanisms of reduction in a lab scale. Next slide, please. We also learned that if we add some non-conductive oxide phases into our iron oxide suspensions, for example, aluminium, magnesium, titanium oxides, if the content is quite high, we will have some problems. We will have the partial blocking of the electrochemical active surface of the cathodes that eventually will lead to decrease of the Faraday efficiency. It can decrease until to 20%, and sometimes, for example, when we tried with titanium, we didn't even obtain metallic iron. Next slide, please. So as summary, we can actually obtain from pure hematite suspensions high Faraday efficiency. So it's iron electrowinning from pure hematite suspension is feasible. It's also feasible under intermittent conditions provided by renewable sources, especially if we have cathodic protection, the residual current. It's possible to use either bulk cathode or suspensions. Of course, suspensions are much more suitable for industrial processes. It's feasible to use magnetite as a feedstock for the suspensions mode. And we can consider including non-conductive impurities in a small content. If it's high, it will partially block the surface of the cathodes and it will lead to low Faraday efficiencies. So it's all from my side. Thank you for your attention.
Okay, thank you very much, Daniela. There are some questions. Okay, one of them we have. Is there any possibility of obtaining iron alloys from the electrowinning process?
Yes, there is the possibility of using iron nickel-based alloys, and also probably copper and cobalt. For other metals, we need to check Purbeck diagrams, but in principle, for these three metals, it's possible to perform iron-based alloys, yes.
Okay, thank you, Daniela.
Let's
continue, although there's an additional question we will give for the end of the webinar. The next presentation is by Professor Dimitrios Panias from the National University of Athens, and who will present the alternative feeding materials, the current status and future perspectives. Okay, Professor Dimitrios Panias is a metallurgical engineer who graduated from the School of Mining and Metallurgical Engineering of the National Technical University of Athens, TUA, in 1984. He completed his PhD on gold pyrometallurgy, also at NTUEA in 1989, and he's currently professor in extractive metallurgy and director of the Laboratory of Metallurgy, and also head of the TESMET, Technologies for Sustainable Metallurgy Research Group. He has he has 240 publications and more than 100 in peer-reviewed journals, with more than 6,500 citations with an H index of 39. So, Professor Panias, when you want.
Thank you very much, Ignacio. Except of using iron oxide, pure iron oxide phases or iron ore in the Siderwin process, we try to use also alternative secondary raw materials that contain high amount of iron. The most studied raw material that we tested in the Siderwin project was the bauxite residue. Bauxite residue is a byproduct of aluminum refining, with the bioprocess. It is produced annually at the global level in huge amount, more than 1,080 million tons. And at the European level, it produced annually at a level of 7 million tons. The sample that we use was generated in the Mytilineos plant in Greece, and contains a high amount of iron oxide, almost 45%. Also contain, let's say, 19% of alumina, 7% of silica, 10% of calcium oxide, 3% of sodium oxide, and let's say 7% of titanium oxide. It has a complex mineralogy. The main iron-bearing phases are hematite and goethite, where aluminum, silicon, calcium, and sodium exist in other phases like cancrinite, like hamosite, like hydrogarnet. And of course, titanium exists mainly as a calcium titanate, as rutile and as anatase. Next, please. The bauxite residue has complex mineralogy, as I told you before, and is extremely fine with a mean particle size lower than 5 microns, but is strongly agglomerated. And the most important is that the iron phases actually has been trapped inside the bauxite residue matrix, as you can see here. The next, please. The cyclic voltammetric studies made in bauxite residue showed us all the peaks and the electrochemical characteristics showed also in the iron ore electrolysis, which means that firstly we have an area very close to 1 volt versus mercury oxide reference electrode, where we have the transition of hematite to magnetite. Then we have higher currents, where we have the deposition of iron, and at lower negative values, we have the generation and the evolution of hydrogen due to water reduction. The next is one of the most important characteristics shown to us by cyclic voltammetric studies was that the currents that are passing are substantially lower in relation to the iron ore and iron oxide phases electrolysis. For this reason, when we try to do electrolysis at the conditions where the iron ore electrolysis is taking place, at high current densities, the current efficiency we took was extremely low, very close to 30%. And by decreasing the current densities, we achieve higher current efficiencies, reaching moderate values of almost 50%. The reason is that at extremely high current densities, the cathodic potential is extremely low, and then we have intensive hydrogen evolution reactions. Then, the next please. Then we try to increase the current efficiency, and for doing this, we did several experiments by changing the electrolysis temperature, reaching temperatures such as 130 Celsius degrees, which is almost 10 degrees lower than the boiling point of the electrolyte we are using, which is a concentrated 50% per weight sodium hydroxide solution. As you can see, from 70 Celsius to 130 Celsius degree, there is an almost linear increase in current efficiency, reaching values close to 70%, and then we have again a decrease in the current efficiencies. The next, please. The most important characteristic is that when we try to do long-term electrochemical tests with a duration more than 2-4 hours, in this case, we have the phenomenon of gradual decreasing in current efficiency, reaching at the end a plateau at a current efficiency value, which is almost half of the current efficiency we had initially at the 2-4 first hours of electrolysis. If we see the deposition in the cathode, actually we can see two layers of deposit. The first one has a very thin size, let's say 6 to 7 micron, and the second one is the dendritic development of the iron crystals. The next, please. By doing examination in scanning electron microscope, we realize that after the first layer of deposition, which was pure iron metal, we had the blockage of calcium titanate phases, and the calcium titanate phases polarized the electrode toward negative values, making the current efficiency lower. So this is a drawback that we ought to overcome in order actually to use the bauxite residue as a raw material in the Siderwin project, in the Siderwin process. The impurities we have the potential to polarize the cathodic electrode, and with this way to decrease the current efficiency. The next, please. Another alternative material we used was the mill scales coming from the steel rolling mills. The mill scales are more or less pure iron oxide alternative raw material. The next, please. With a mineralogy mainly hematite, magnetite, and wustite. The next, please. The cyclic voltammetry showed exactly the same behavior as in iron ore electrolysis, with current densities very high and comparable with the ones of iron oxide. The next, please. And you can see that by doing several tests in the area where the iron deposition is taking place, we achieve actually current efficiencies very high, higher than 90%. And as we are going to higher current densities, we can achieve a higher efficiency, current efficiency in the process. So the mill scales is a very good raw material that can be used in the Siderwin project. Of course, we ought to take care that in some cases there is high amount of oils in mill scales, and the oils passivate the particles of iron ore, and it is necessary a pre-treatment stage to remove the oils and the organics. And the other case is, in some cases, the mill scale is composed from wustite. Wustite is not a good iron oxide source for Siderwin electrolysis, and for this reason, in this case, it is necessary to do an oxidic pretreatment in order to oxidize, to hematite, and then do the electrolysis. But in any case, the mill scale seems to be a perfect material that can be confront all the standards of Siderwin process. The next, please. We tested also iron sludges coming from the nickel hydrometallurgy and exactly from the purification of nickel chloride solution by using chlorine and nickel carbonate. The iron sludges contains high amount of iron, almost 50% iron, but also contain impurities like nickel, like cobalt, like copper, like arsenic, and precious metal like gold, silver, and PGMs. The mineralogy is mainly iron hydroxide, and please, the next. And the sample we got, the main phase we found was academiide, which is beta iron oxy hydroxide. The next, please. The voltammetry we did is directly comparable with the one of pure iron oxide suspensions. The next, please. But the test we did showed that the iron deposition is taking place at lower cathodic potentials. The next, please. And for this reason, the efficiencies we have achieved till now was low to moderate. Also, iron sludges are a good raw material, but it is necessary to find again the way to purify and to remove some metals that polarize the electrode, and with this way we can increase the current efficiency. The final, please, the next one. Okay, here we can see the deposition. In case of the iron sludges, the deposit was porous with small spherical iron crystals, and in contrast with the typical deposition for iron ores, which is well-defined dendritic crystals. And this is this indicates that the impurities affect and polarize the cathode, making the hydrogen evolution feasible, and thus decreasing substantially the current efficiencies. The next, please. Also, we tested ferritic slugs coming from copper and ferronickel pyrometallurgical processing. Generally, the ferritic slugs contain high amount of iron, almost 45%, and of course, high amount of silica. Iron exists in bivalent states, and the main phase is ferrite, iron silicates. The material is amorphous. The material that we tested was amorphous. The next, please. The cyclic voltammetry showed again that there is an area which coincides with the area that we had seen also in the previous alternative materials, where iron can be deposited. The next, please. We did several experiments, and we showed that the efficiency of the process, the current efficiency, is low, very low, and the reason, the next phase, the reason is that in highly concentrated sodium hydroxide solutions, we have dissolution of silica, of amorphous silica, and then we have the polycondensation and polymerization of silica that increase the viscosity and thus decrease the conductivity and hinders the iron deposition. The next, please. The general conclusion is that we tested a lot of alternative raw materials that contain high amount of iron and are coming from different industrial and metallurgical processes. The conclusion is that all of them have the potential to be used as alternative raw materials inside the wind process, but as impure materials that contain high amount of iron but also high amount of other impurities, it is necessary to pre-treat it in order to remove some impurities that we have very well defined. We know that they affect negatively the electrolysis process, decreasing the current efficiency. So at this moment, we know the raw material that we can feed the Siderwin process, and we try to overcome all that difficulties that I showed you before. Thank you very much for your attention.
Okay. Thank you very much, Dr. Panias. There are one question. What are the prospects for alternative raw materials in Siderwin technology?
The prospect is positive because, as I showed you, all the alternative materials we tested can actually be electrolyzed and produce pure metallic iron. But secondary materials and residues of other industrial and chemical and metallurgical processes, they contain some other metals, which in the case of electrolysis are impurities, actually non-electroactive impurities that are attracted on the surface of the electrode or on the surface of the cathode, and for this reason polarize the electrode to negative potentials. So, due to this effect, in some cases, in order to have high current efficiencies, it is necessary to decrease the current that we are passing, and for this reason to decrease the process productivity. And in some other cases, we cannot do this, and we have to find a compromise in between the iron deposition and the hydrogen evolution. But we know that in any case, we ought to pre-treat all that secondary alternative raw materials in order to remove the impurities that cause this problem.
Okay, thank you. Let's move to the next presentation, that is iron production by electrolysis at pilot scale. And this will be a joint presentation by Thierry Conte from CFD Numerics and Salah Tounami from ArcelorMittal. Thierry Conte is a fluid mechanic engineer and founder of CFD Numerics in 2008. CFD Numerics is a French company specialized in computational fluid dynamics for several sectors and industries such as energy, aeronautics, automotive, medical, process metal production, and so on. And Salah Tounami graduated from the Lorraine University with a PhD degree in mechanics and energy. During his thesis, he worked on the durability issues of proton exchange membrane fuel cells. And after completing his thesis in 2022, so you can start to read the presentation.
Okay, so if you can move to the next slide, please. Okay, so first, thank you, José Ignacio, for the presentation, and good morning or good afternoon to everyone. So in this part, we are going with Salah to present you how we define and we design the pilot set for Siderwin, mainly using numerical simulations. And Salah will present you what are the key process parameters for the electrolysis and explain you the main assessment regarding cell energy consumption. Next slide, please. So first, regarding the Siderwin pilot itself. The first question we had during the first phases of the project was to define an optimal electrowinning cell. So because as you have seen before, we had to deal with electrolysis process that is going to generate a large amount of oxygen bubbles in the cell. And one of the main major issue of this cell in the cell is to get some oxygen accumulation in the cell that could lead to a dramatic loss of efficiency. So to avoid these issues, we have decided to rely on CFD simulations. And just to remind you, CFD means computational fluid dynamics. It means that using numerical simulation, we can simulate the flows, and especially two-phase flows in the cell, first to understand how it works, to analyze and to optimize the designs of the cell. So regarding the numerical models in the project, we decided to split the work in two steps. The first one was to define the relevant methodology to calculate two-phase flow. And the second one was to apply the defined methodology to design the cell. As you can see, and I will show you later some detail of the design we have to define with simulation. For example, the anode design, the cell angle, the degassing device, some distribution of the inlet distributor to get a very smooth flow in the cell, or the pump specification. Next slide, please. So regarding the oxygen bubbles management, as you can see on the left side of the picture, we can see that this is a scheme of very conventional electrowinning design with some vertical plates and bubbles generated on the anode. And as we have to deal with a very long cell, almost 3 meters, if we had used such a design with just vertical plates, we would have get some troubles regarding screening effect, meaning that some bubbles are generated on the anode, and then we do a kind of screening effect on the anode with a very dramatic loss of efficiency. So we had to define a more innovative design to address different challenges. The first one was to keep a short distance between the anode and the cathode to optimize the electrolysis efficiency. Of course, as I will show you later, we had to deal with electrolyte and bubbles counterflows to avoid bubble accumulation. But we wanted also to take advantage of the gas leaf effect. I mean with gas leaf effect that when the bubbles of oxygen are going up in the cell, they will entrain some electrolyte, giving some momentum to the electrolyte that could be used to have some gain in terms of efficiency. And finally, the main important thing is to perform a very efficient gas electrolyte separation so that we can separate the electrolyte from the gas and send back to the cell a pure electrolyte. Next, please. So in the very early stage of the project, the design installation, the general installation was defined, as you can see on the left. And with the numerical simulation, we concentrated on the electrowinning cell itself, as you can see in the picture in the middle of the screen. We made some optimization with CFD models on the electrowinning cell. And then using the main conclusions of these numerical simulations, we were able to define the final pilot cell, as you can see on the right picture. Next, please. So how does it work in the cell regarding flows? As you can see, we have some electrolytic flow from the left to the right coming from the pump. This is the main electrolyte flow. This flow is going inside the cell, above the cathode and just below the anode. And in this area, on the right of the picture, you have the electrolysis process, which is taking place, generating some bubbles, which are going up, and they are going up on the top of the picture with the electrolyte. And on the top left of the picture that you can see, we have at the top some flows with bubbles going up. We have a specific design, dedicated design to remove the bubbles from the flow and to send back a pure electrolyte to the cell. Next slide, please. So we had several objectives with CFD simulation. Of course, as for any hydraulic device, we wanted to reduce the general pressure drop through the cell. We wanted also to design and to define a good shape for the electrolyte inlet distributor to ensure uniform flow entering the anode space. We wanted also to the previous one. We wanted also to determine the optimal angle. There is something wrong. If you can go back to the slide number 60.
Salah, I think you are moving your mouse. Don't touch anything, please.
Okay, thank you. One of the important things was to define the optimal cell angle. I mean, we have to decide between a vertical cell or with a cell with a certain inclination to control the buoyancy force and the gas lift effect. Of course, we made some simulation to determine the optimal design for the anode and to avoid the bubbles accumulation. And finally, to define a good device to separate the mixture flow of bubbles and electrolyte. Next slide, please. So we made a design with a honeycomb anode with a certain cell angle. We made the design of the cell assuming a very high Faradic efficiency because we had to start with some assumption at the beginning. So we assume that we had a quite high efficiency between 90–95%. And we succeeded in defining a design of the cell that could avoid accumulation of oxygen bubble in the cell while keeping a very short distance between anode and cathode. We also succeeded in designing some devices to allow a smooth electrolyte gas counterflow with an appropriate gas lift effect. Next slide. And we were able to define and to check that the proposed design for the separator at the top part of the cell was efficient to separate properly the gas and the electrolyte. Next, please. Finally, on the defined design, we have decided to evaluate what would happen if the Faradic efficiency was lower than 90–95%, for example, reducing to 70%. And when the Faradic efficiency is decreasing, we start getting some hydrogen bubbles generated on the cathode. And these hydrogen bubbles could lead to some troubles in the cell functioning, because what we can have with hydrogen bubbles is these bubbles are small enough to be entrained by the electrolyte in the main loop of the cell. And so this was a concern that we had to fix. and that we were able to identify using CFD simulation. So next slide, please. So as you can see here, this is the final design of the cell with the honeycomb anode with the graphite carbon. And from this point of the presentation, I will let Salah present the main results on the pilot operations. And I'll be available at the end of the presentation for any questions regarding the simulations and the design of the pilot. Thank you all for your attention.
Thanks, Thierry. Hello, everyone. So in this slide, we can see the electrowinning cell in its entirety, and we can see also the cross-section view of the cell with the different components. We can see the cathode made of the graphite to avoid a sticky deposits, and we have the anode made of nickel with a honeycomb shape to allow the gas to leave the cell. And also we can see here that we have channels on the cover of the anode to let the gas to leave the cell to the degasser. And between the anode and cathode, we have an empty space with 1 centimeter of thickness for the circulation of the electrolyte and for the growth of the iron plates. Next slide, please. So the picture at the left showed the Siderwin pilot installed on the ArcelorMittal site in Mézières-les-Metz. And the preparation of the trials on the pilot is done in 4 steps. The first steps is the preparation of the electrolytes in the mixing tank by mixing soda with hematite and heating the solution to 110 degrees Celsius. Second step is the filling the closed loop with electrolytes, as we can see here. The third step, the circulation and the heating of the electrolytes in the loop. And here you can see we have a pump for the circulation of the electrolyte, and we have a heating band for the heating of the solution. And when we reach the temperature of 110 degrees Celsius, we start the electrolyze. Next slide, please. Yeah, and we also worked with Technalia, who developed the Pordina tool using the commercial software LabVIEW, and it was developed during the design and development process of the pilot plants to assess the feasibility of the specification in terms of flow and the mass balance and heat losses. Once the pilot cell was in operation, a data-based model using the real data of the process was also developed to predict the Faraday yield of the cell and to optimize the operation parameters. Next slide, please. Yeah. In this section, we will see the 2 case process parameters required for efficient electrolysis of iron oxide into metallic iron. Yeah. Thanks. So the first parameters is the good evacuation of gas, as we will see. So here we have the plate produced during one of the first trials carried out on the pilot Siderwin, with a cathode of a surface of 2.75 meters square. And we can see that during this trial, we obtained a very brittle deposit, and the thickness was very of the deposit was very small. And the fragmented deposit of made a contact with the anode and made short circuits between the 2 electrodes So large current goes in short circuits between the two electrodes without being using for iron electrolyzers. So to improve the gas evacuation, we reduce the concentration of hematite in order to decrease the viscosity of the solution, and also we reduce the pilosity of the electrolyte. And in the figure at the right, we can see the iron deposit obtained with this process parameters modification. And we can see that the iron deposit was more thicker. We had a thickness of 1 millimeter and less fragmented. But to have a good iron deposit for the gas management is still needed. Next slide, please. And to do this, we thought of reducing the size of the cathode to 1.25 meters square instead of 2.75 meters square by removing pieces of anode and cathode from the side of the cell outlet, as we can see here, in order to decrease the amount of gas produced and also to increase the length available for gas extraction. And after this adjustment, a 1.25 meter square iron plate had successfully been obtained with a thickness of 1.5 millimeters and a weight of 15 kilograms. And the plate was homogeneous, not fragmented, and easy to separate it from the graphite cathode. Next slide, please. However, dendrites have been formed on the plates at the electrolyte inlet, as you can see in the figure here. This part is the outlet of the electrolyte, and this part is the inlet of the electrolyte, and this part is the outlet of the electrolyte. And this dendrite grow and made contact with the anode, causing short circuit between the two electrodes. And to prevent their formation, we added a big plate before the cathode at the electrolyte inlets in order to improve the electrolyte flow at the cathode when the electrolyte arrived in this area. Next slide, please. And in the figure at the left, you can see the cathode and the peak plates that we added before the cathode. And the trial performed with this modification resulted in a plate without dendrite, homogeneous and not fragmented, as you can see on the slide. And the energy consumption of the cell during the different trial carried out on the pilot with the graphite mini cathode is presented here. And on this figure, we can observe that the specific energy of 2.7 megawatt-hour per ton produced is achievable under optimized condition, as in case of trials 2, 3, and 6. On the other hand, in the case of trials 1, 4, and 5, the specific energy was high due to short circuits related to dendrites or to some equipment issue leading to the interruption of the trials. In conclusion, yes, next slide, please. In conclusion, we have seen with the theory that a comprehensive method using CFT was used to design the optimal cell and identify the potential bottlenecks. And then we have seen that equivalent iron plate of 1 pound 84 meters square is achievable with an easy separation from the graphite cathode. But to have these results, there are two case process parameters should need to be validated. The first parameter is a good gas evacuation. The second parameter is the uniformity of the electrolyte flow. And finally, we have seen that the specific energy consumption of the cell about 2.7 megawatt hour per ton produced was achievable under stable operating condition. Next slide. So thank you for your attention. If you have any question.
Yes. Okay. Thank you, Thierry and Salah. Yes, there is time for just one short question. What is the Faraday efficiency that you obtain in the pilot cell?
The Faraday efficiency is between 85 and 90%.
Mm-hmm. Okay. Thank you. So let's move to the next presentation. That is the flexible potential of Siderwin process for the future European power system. This is going to be a presentation by Morgan Barberus from EDF. And Morgan works as a research engineer at EDF R&D, specialized in energy efficiency and decarbonization for the manufacturing industry. Morgan has been coordinating the contribution of EDF in the project since the beginning of this. So Morgan, it's up to you.
Thank you, Jose. Hello, everybody, and thank you in advance for your attention. So now we will talk about the integration of Siderwin at an industrial scale in the European power system in the future in 2050. And we will see the consequences in terms of flexibility and the benefits for the systems. You know, because you know that the development of the renewables in Europe will lead to more intermittency on the systems. So we will require more flexibility in the system. And this is the quality of this technology. So we'll talk about that. On this slide, you can see the main contribution of our company, EDF, in this project. Our contribution was first to analyze the impact of this technology at an industrial scale in the future European power system. So this was the first step of our contribution, and the second step was to check on the pilot the ability to operate really in on-demand mode, so to modulate and interrupt the electricity consumption. So next slide, please. Sorry, there is an animation, so you have to click. Thank you, sorry. Okay, so for the first part of our contribution, to analyze the impact of the Siderwin development for the power system, we had to create a model of the power system, taking into account the design, the connection between countries, the electricity mix, etc., the demand. But we have to take into account an important data collection, because it was important for us to be consistent with the European vision of the future, but also with the vision of the European grid operator. So we have made a model of this system in 2050, and we have integrated the Siderwin plants in this model. So it is a parametric assessment with, depending on the plant's location, the climate variations, because you know that there is a different scenarios considering the evolution of the climate, and also the fuel prices, the evolution of the CO2 price, assumptions on the plant outages, etc. So we have made a model and a parametric assessment in order to quantify the impact of Siderwin on the system. So next slide, please. So on this slide, you can see the maximum trend. In other words, we have considered a scenario in which all the blast furnace in Europe are replaced with an electrolysis technology like Siderwin. So it could represent up to 471 terawatt-hour per year in 2050. So this is an additional electricity demand if we want to develop Siderwin at an industrial scale in order to produce the same quantity and of steel with, of course, an evolution of the market. And it's very important because it represents around 12% in average of the European electricity consumption in 2050. So to meet this new demand, we have to consider additional low carbon electricity sources, and for that we have to choose electricity sources taking into account the potential in Europe, and also the production profile, because we have to select a production profile consistent with the consumption profile of this kind of process. So we have made three scenarios: one with additional nuclear power plant, another with additional offshore wind, and another which is a combination of these two energy sources. So next slide, please. On the next slide, you have an example of what you can see with the model. So you can see the behavior of the system day by day, hour per hour. This is a representation of 1 week. And you can see the solicitation of the different generation technologies to meet the demand, and also the activation of the flexibility capacity of Siderwin. And the key message here is to see that in our assessment, Siderwin could represent up to 39 gigawatt of flexibility, and this is very important. And we will see the consequences, the main consequences, on the next slide. Please, next slide. So on this slide, you have two graphs. The left one is more detailed, so we'll have a look on the right one. You can see that the graph is split in two parts. On the left, you have the scenario with Siderwin but without flexibility contribution, and on the right you have a scenario with a flexibility contribution, and you can see that 0 is a scenario without Siderwin. So this is 2050 but without Siderwin. And if you want to integrate Siderwin in the system, you will have to add additional, of course, power plant, but you will also introduce more flexibility, intermittency in the system. For example, if you are in an offshore, total offshore scenario, so you will need additional gas plant to balance the system when the demand is higher in comparison to the production, and if you don't have enough flexibility potential in the system. So in this scenario, without flexibility, you have to add additional peak load means gas power plants. And on the right, you have the conclusion with the contribution of Siderwin as a flexible capacity. And you see that the development of Siderwin gives the opportunity to replace gas power plant. So this is the main benefits of the Siderwin in the system. So next slide, please. You can click because there is some animation, but this is the details of the conclusion. But the key message here is that the conclusion of our study is that the design of the European power plant enables the integration of the Siderwin technology at an industrial scale. It is possible. An industrial development will require, of course, additional low carbon power plants, but will avoid to invest in peak load gas plants. This is important, and that represents important savings for the systems, savings in terms of investment, of course, but also in terms of CO2 emission, because you don't have to consume gas. So in all our scenarios and in all the variations we have in our conclusion, we observe a decrease in the carbon footprint of electricity generation in Europe. This is the key message of the study, and this is the real benefits of Siderwin as a flexible capacity. Next slide, please. Okay, so this is to say that if you want more details on this study, of course, there is a deliverable of the project, but also there was an article written for the European Council of Energy Efficiency. You can find it online. So quickly, I will next slide. I will talk about the second part of our contribution. The second part of our contribution was to check the ability to operate in on-demand mode. So for that, we had to test the pilot. So we have to identify the load curve. So in other words, the electricity consumption profile of the pilot, and we have to analyze its behavior and also to interrupt and modulate some equipments, but not all the equipment, because we have also some equipment that need to remain activated for security reasons. So we have realized this test with ArcelorMittal, and the conclusion of this test is that you can go to the last slide if you want. The conclusion of this test is that the Siderwin technologies have a flexibility potential. This is validated, and with a good reactiveness, and without duration constraint except rebound effect, because if you stop a heating element, of course, when you want to restart, you have to consume a little more to recover the temperature. But the conclusion is that it's possible to operate in an on-demand mode, and it is possible to operate for Siderwin on the most profitable demand-side response market. So this is a good news for the development of this technology. Thank you. This is finished.
Okay, thank you very much, Morgan. Yes, some time for a quick question. In your model of the future power system, why have you chosen only nuclear and offshore wind energies to meet the Siderwin additional demand?
Yes, it's as I said, the electricity consumption profile of a continuous process like Siderwin is very flat. So to meet this demand, we must consider an additional electricity source with quite the same profile. So to do that, you don't have many possibilities. So nuclear is okay. Hydropower is of course okay, but the problem is that in Europe, in Western Europe, there is no significant potential additional capacity. So this is problematic. And in the renewable category, only the offshore wind energy is possible, because there is a lot of intermittency with the other kind of renewable sources. So that's why we have made only 3 scenarios: one with nuclear, another with offshore wind, and the last one with a combination of the 2 sources.
Sorry. Thank you very much, Morgan. So let's move to the next presentation, that is, what is the environment impact and cost of steel decarbonization with Siderwin? And it's going to be presented by Roland Kaman from Recoy. Roland has worked for Recoy since 2017. Recoy is a Dutch company specialized in valorizing flexibility in industrial production processes against the background of volatile electricity prices. Within Recoy, Roland is responsible for the innovation projects that Recoy is involved in. And within Siderwin project, Recoy has the responsibility for the techno-economy study. For today's webinar, Roland is going to talk on behalf also of Quantis with respect to the environmental impact, as well as on the techno-economical study. So Roland, it's up to you.
Thanks, Jose. Good afternoon, everybody, and good morning, dependent on your time zone. So first of all, I'll talk on the decarbonization potential of Siderwin. Again, as Jose just mentioned, this is work done under the auspices of Quantis. So in this slide, in the first couple of slides, I'll show you sort of on a high level, macro level, the contribution that the steel industry has to global greenhouse gas emissions. This number has already been mentioned before. I show you here a Schenke slide from chart from 2016, but since then not much has changed. The iron and steel industry is responsible for about 7% of global emissions. Next slide, please. If we translate this to a European context, the European Net Zero Roadmap targets a 30% reduction in 2030 compared to 2018, and being close to neutrality by 2050, using, of course, also CO2 removal options. And the steel sector in the sort of light brown coloring on the graph, which talks about the total industrial contributions in terms of CO2 reductions. The steel sector has its part to play and will follow the reduction pathway with proper policies, as already been mentioned earlier by ArcelorMittal in its introductory contribution to the webinar. And the European Green Deal sets a scope for creating new markets for circular products, climate neutrality, for in sectors such as the steel and the cement and basic chemicals. Next slide, please. From a more the position that Europe has in a more global perspective, again, Europe is responsible for about 10% of the steel production in 2020 Europe-wide. The total number is about 2,000 million tons, and again, Europe is responsible for about 200 million of those. And by developing innovative technologies to decarbonize its steel sector, the belief is that Europe can inspire other steel producing countries to go and walk down similar pathways. What also helps is, of course, the ETS system that Europe has introduced in terms of pricing the emission of carbon. So in total, a pathway for decarbonization route for the steel sector. Next slide, please. Moving more and more towards Siderwin then, as you're probably familiar in terms of carbon footprint classifications, there are 3 scopes. On the one hand, there's scope number 1, which relates to direct emissions from the production process itself. And in the context of Siderwin, of course, by electrifying the steel production, not using coke anymore, cokes anymore, it can help reduce direct emissions of the steel sector. It is, however, using electricity, and that relates to Scope 2 emissions, looking at purchased power. However, because of the ongoing decarbonization of the electricity sector in Europe, this will further drive down emissions of the steel Siderwin production process by relying on more and more decarbonized electricity. And then there's a third scope, Scope 3 emissions, that looks at the overall value chain of in general a production process. And for Siderwin, we've looked at that as well. And when I say the value chain, I look at specifically the upstream side, or we have looked specifically on the upstream side of the Siderwin process. In other words, looking at the raw materials that go into the Siderwin process, and that very much in the more traditional BF-BOF route, a lot of lime is being used. By reducing the reliance on lime and by focusing on the content of the raw materials going into the process, Scope 3 emissions will be reduced as well. Next slide, please. Since there's a heavy reliance on electricity into the Siderwin process, it is important to, looking forward to the year 2050, to look at various electricity mix scenarios in a way similar as to what Morgan just reported on, and the way that EDF has defined scenarios. We've defined for Siderwin two scenarios. One, the one that EDF has proposed, as just reported on by Morgan. And then we've also looked at a renewables only scenarios for Siderwin, which is reliant on 100% renewable mix. And we've anchored that, as I'll show in the next slide, we've anchored the, sorry, if we can just go back to the previous slide, I beg your pardon. We've anchored the contribution in terms of moving towards reduction of carbon emissions by looking at the traditional process, that's the BF-BOF route. And in that case, we also need to have a current scenarios for the electricity mix, and that's shown on the left-hand side. Next slide, please. And this slide shows the carbon footprint of Siderwin in a number of electricity scenarios compared to the reference technology, the blast furnace BOF route. We've looked at actually for the reference scenarios at two steel grades, one low alloy steel and one non-alloy steel. But if we look at the low alloy steel product, Siderwin, dependent on the assumed scenario for electricity in the year 2050, can reduce either 60 to 74% reduction in terms of carbon footprint. And this has been, again, as I said, dependent on the electricity mix. But what first and foremost shows is that the Scope 1 emission is completely gone from the Siderwin route, and this is of course because electricity is used and not the traditional coke route that the BF-BOF route relies on. And secondly, that the Scope 3 emissions have been reduced as well. And for the renewable scenario electricity mix, the Scope 2 emissions have been reduced as well. And this is of course purely due to the fact that it's 100% reliant on renewable energy. Next slide, please. Another way of looking at the carbon footprint is to zoom in on the various sub-processes of the Siderwin technology, and then apportion the footprints per sub-process according to Scope 1, 2, or 3. And what it shows here is that Scope 1, that's in the lower bar here, is 0 in terms of carbon footprint for every sub-process. but that for scope 3 and 2, there is a different outcome in terms of footprint for the various sub-processes. In terms of scope 2, in other words, looking at the electricity, of course, the electrowinning part is most responsibility for the limited amount of carbon footprint from a scope 2 point of view. And by the way, we're looking here at the non-renewable mix scenario as related to in the slide before. So for scope 2, it's the electrical winning sub-process that is responsible for most of the scope 2 emissions. And if we look at scope 3, it is both the furnace melting, casting, and reheating exercise or process, and the iron ore extraction process that is responsible for the main part of scope 3 emissions. And just to highlight that, the fact that there is an iron ore extraction is because we look for scope 3 at the whole value chain that Siderwin is involved in. And here, of course, on the iron ore extraction side, there is a fairly large amount of carbon footprint still active, as is when we look at the melting, casting, and reheating, because we use a lot of raw materials going in, and there's an element of scope 3 emission there as well. Please, the next slide. We've looked at not only the carbon footprints in terms of environmental indicators, but we've also looked at human health aspects. And for Siderwin, we've mainly looked at the respiratory inorganics element, which looks at the particles emitted during the coking process, insofar as you compare it to the original BF-BOF route. If you look at the Siderwin route, we have observed, or the analysis shows a 25% reduction in the elimination of these respiratory inorganics. And also on top of that, one has looked at water consumption and land use. However, it was shown that that has a relatively less material impact because steel production uses much less of these agroforestry products, as they are officially called, and land use, such that the slightly increased use there more than offsets the benefit in terms of the human health aspects. Next slide, please. So in summary, insofar as the steel decarbonization route is concerned, the potential of Siderwin, we see an up to 74% footprint reduction per ton in the Siderwin technology. We see a reduced impact on human health, and we believe the Siderwin technology is a very potentially a very interesting route for reducing footprint of the steel sector, and helps in contributing to the objective of the European Commission in its neutrality objective for 2050. So that concludes the decarbonization part of my presentation. We'll now move on to the economic costing side of things. Next slide, please. And what we've done to rehash what you've already seen, these are the various sub-processes of the Siderwin process. If we can move to the next slide, please. What we have done for the modeling of the economics of the whole route is to simplify to this straightforward picture with the Siderwin process in the middle. We've looked at the cost data currently available for all these various sub-processes, cost data essentially consisting of CapEx and OpEx figures based on the materials balance analysis done by ArcelorMittal. We then considered the main inputs into the main economic inputs into the system, which are essentially the electricity and the iron ore. There are a number of other raw materials as well. However, they're not of a material impact such that they will significantly impact the overall analysis. So it's mainly the electricity price and the iron ore price which will have an impact on the input side. And on the output side, we looked at the sales, the value of the products coming out of the Siderwin process, which is mainly hot rolled coil, and by far again that is the main beneficiary towards the revenue side. There's some byproduct being produced as well with a certain value, titanium and oxygen, for example. But again, in the overall materiality of that, it is rather insignificant. I will also show you that we've considered in the economic model a number of other products, but for the core analysis of the Siderwin process, we've looked at this model. Next slide, please. And the economics is based on a straightforward NPV analysis of the cost data, as I've just highlighted, and the revenue streams. Cost data is, as mentioned, based on CapEx and OpEx, based on a life cycle costing analysis of the individual process steps, as well as the cost of iron ore and energy. The revenue stream consists of the sales of the HRC product, the steel product, flexibility income, and possibly sales of green certificates. I'd like to highlight now what I mean by flexibility income. Next slide, please. As Morgan has already highlighted, the Siderwin process is within limits a highly flexible process. In general, steel production is considered a 24/7 process for 365 days of the year, other than days of planned maintenance and outages. But within limits, again, the Siderwin process is flexible. And the assumption we've based our analysis on is that for around 5% of the operating hours per year, Siderwin is able to ramp down the production. And what we have done is in a different route than the EDF route, which has been looking at a more macro analysis of the value of flexibility, i.e. looking at the avoided investment in gas peaking plants. We've looked at a more bottom-up approach by looking at flexibility markets available. In other words, the flexibility that Siderwin has can be valorized on various electricity markets that help maintain the integrity of the transmission system wherever Siderwin plants are being planned to produce in the future. If we can move to the next slide, please. I'll highlight that in a bit more detail. So the blue line shows the base operation of Siderwin at as I said, at the base load at the top there. And in the red, I've shown what is called an imbalanced electricity price. And an imbalanced electricity price, without going into too much detail, shows a short-term electricity price. When I talk about short-term, I mean literally short-term, within the hour or within 15 minutes even. In more or less all of Europe, the electricity price is based on 15-minute slots. And given again what Morgan has identified earlier, the Siderwin technology, as also shown in the pilot situation, is able to react fairly quickly in terms of ramp down. And this is good because the electricity price, this imbalanced electricity price, is a very volatile price, which can move up and down within minutes, from very high positive to very low negative. And if one is able to predict and being able to predict the electricity price and being able to react to these volatile electricity prices, one can make money out of that because that flexibility is valuable. And so what we have done is we've built a model based on an activation price level, because if you ramp down the baseload production of Siderwin, you lose the income of steel products. And since you assume a 24/7 operation, you're never able to make up for that again. So you should only ramp down Siderwin if the electricity price is sufficiently high to make up for loss of revenues of your steel product. And that is what we call the activation price. And our model shows that, admittedly, based on history, the last 5 years, that in all of Europe, so we've built a model that looked at the value of this type of flexibility in all the various European countries at the various electricity price markets. If you have this type of flexibility, you're able to generate an additional income literally in hundreds of millions per year for a typical plant size, a conceptual plant size for Siderwin. So if you can go back to the previous slide again. As I've shown in the bottom bullet point here, is that based on this analysis, we believe, and the difficulty is of course in extrapolating that to the future, but there will be flexibility needed in the future, and Siderwin will have that flexibility, and we believe that this flexibility is highly valuable. And on a European level, we believe that this can generate an income stream of literally hundreds of millions per year for the Siderwin technology. If you can move to the slide after this one. To conclude that based on current technical and economic data, the Siderwin technology has a very high potential to be profitable at the time of commercialization. And it is certainly profitable enough based on current assumption to be moving it to the next TRL level, moving closer to commercialization. We believe, as stated earlier, that the economics can be significantly improved through the valorization of flexibility. And as I said, as the technology moves through the different levels of maturity, the expectation is that the cost fixtures will improve through learning and thereby enhance the economics. There is an additional potential benefit over and above the valorization of flexibility through the issuance of carbon credits. However, I have to admit that the value of these are, at the time of commercialization of Siderwin, are very difficult to assess, mainly because at the time of commercialization of Siderwin, the whole industry will be hopefully greatly environmentally friendly. So the relative value of Siderwin and its potential carbon credits is very hard to assess. But it's something that we believe should be taken into account and be looked at. And then finally, also alluded to by Morgan just now, whilst the electricity sector, European electricity sector, should be able to accommodate a high electricity demand sector such as Siderwin, what we do believe is that the spatial allocation of where these plants will be different from today. It will probably be much closer to wind and solar parks. So, for example, close to in the south, close to solar parks and close to wind parks in the north of Europe, instead of just near waterways, as it currently is. And this means that one will also need to have to look at the integration of such large electricity consumers and the electricity grid, because as we currently see, there is already a large amount of congestion taking place in the current electricity markets, with such a large increase in electricity demand, such as Siderwin. The actual integration of such consumers, large electricity consumers, and the local electricity grids requires close attention. I believe that is my last slide, so thank you very much. And I don't know, Jose, if there's time for one question.
Yes, okay, thank you, Roland. Yes, there is a question, maybe short one. How do you see the Siderwin technology compared with the HDRI alternative?
Right. Well, in terms of flexibility, hydrogen also has a lot of flexibility and will probably attract similar valorization options. The big advantage, though, of Siderwin, I believe, is the fact that it's much more energy efficient, given that you don't have to go through the process of manufacturing hydrogen and then using the hydrogen to do a direct reduction of the iron ore. With Siderwin, you already have the electricity as your input, and thereby it's much more energy efficient. So that's it. Thank you.
Okay. Thank you very much, Roland. So let's move to the last presentation, that is the final conclusion and perspective. So Valentin, please come back. Okay.
Thank you, José Ignacio. So next slide. Can you hear me well?
Yes, yes.
Okay, good. Okay, so let me sum up the main results and the key messages that we have developed during the project. So first of all, we have proven that the Siderwin technology could be scaled up, has been scaled up. We were able to produce 1.25 square meter iron plate, so this is feasible. Of course, well, some key parameters are really key, and we have observed and validated that the gas management, good gas evacuation between the two electrodes is absolutely necessary for having stable operations and guarantee a good parameters. And of course, also the electrolyte flow should be as uniform as possible in order to avoid short circuit because of downtrise formation. And we have validated the electrolysis cell energy use. This was confirmed at the pilot scale. And this was around 2.7 megawatt hour per ton of product. We have also proven that the Siderwin technology can contribute to the future carbon neutral steel making because it doesn't emit direct CO2 emissions. And regarding the carbon footprint, we have calculated that it can reduce up to, well, at least 60% of the carbon footprint and up to 74% depending on the electricity mix that is studied and compared to the traditional BF-BOF route. And this is without compromising the environmental footprint compared to the BF-BOF route. Next, please. We have also demonstrated that Siderwin technology can contribute to the balance of the power system because it's fully electrified primary production, and this is a flexible process operating at low temperature. And so the demand side response mechanism can boost the profitability because we can easily switch on and off because it's operating at low temperature. And for that, the consequence is that the Siderwin technology can contribute to the deployment of the renewable energy sources. And we have also validated the fact that the European power system can meet in the future, will be able to meet in the future the additional Siderwin demand with some, without emitting more CO2 emissions. And finally, we have proven that Siderwin technology can also contribute to circular economy by reusing residues from other industries such as nickel industry, aluminum industry, ferronickel, or copper. So several potential alternatives has been studied. So far, the mill scales from steel industry was the most promising alternative material. But the other alternatives were also promising, and it was proven at lab scale studies that it worked. And some more work must be done before the scaling up of using such alternative feeding materials in Siderwin technologies. So next. And regarding the perspective, so with the results and now at the end of the project, we are confident and we know now that Siderwin is a promising innovative technology for the future of steel because it's not emitting direct CO2 emissions. So direct electrifications guarantee that we won't use any more carbon fossil fuels. So it's thus one of the lowest CO2 emitting technologies today. We have also demonstrated that it's a process function operating at with a high energy efficiency because it's at a low temperature, and we have validated its energy consumption at pilot scale in the project. It's a cost competitive, and thanks to its energy efficiency, it's cost competitive compared to other low carbon steel manufacturing technologies. It's really modular, so it guarantees good scalability. It can easily be adapted to any production capacity of plants by simply, I would say, copy paste different module. So the scale-up can thus be managed with limited complexity, and it's a streamlined operation. As we already commented, it's a quite simple flow sheet compared to other competing technology for which we could require large infrastructure for hydrogen distribution, storage, or CO2 capture. Next. So, since Siderwin technology is a promising breakthrough way of doing steel making in the perspective of being carbon neutral, we have estimated, and based on the vision that we have today and all the assumptions that we have today, that in the future of the steel making, worldwide steel making, and by 2050, if we have a look on the low carbon steel making production, we can see that iron ore electrolysis could have a large part of 17% in the total production of low carbon steel. And still, there will be also almost 60% produced by scrap-based EAF route, and the rest could be produced with what we call smart carbon route and or green hydrogen DRI. But still, we strongly believe that iron electrolysis will be a large part for low carbon steel making. Next. And so we have developed a roadmap. So what could be the next step, and what will be our contribution in the carbon neutrality for steel making? And we are thinking now to the industrialization of this technology, of the Siderwin technology. So coming back a little bit in the history, so the history started later with some pre-Siderwin projects with Olcowin, but even before in the framework of the Olcos program. And in 2017, we had the launch of the Siderwin project, current project. The commissioning of the Siderwin pilot was done last year. And we will keep on doing some trial this year, and well, the project is going to end at the end of this month, and then we will go for designing the next step with the designing of a small pilot plant, and in 2025 we should be ready for and having the go for investment approval for this small pilot plant, and then in 2027. We are expecting the commissioning of this first small pilot plant, and due to the modularity and the easy scalability, because of this module to be copy-pasted, we expected to commission the full-size plant starting from this small pilot plant between 2028 and 2030. And then after 2030, cloning this first plant all around the world at with a million tons scale plant. So as you can see, we really believe that this is a promising breakthrough technology for low carbon steel making in the future. So thank you for your attention, and Jose Ignacio, I think that we have now got some questions.
Yes, so this is the end of the technical presentation of the webinar, but we have some time for questions, and there will be a few of them, so I will try to start reading some of them. There are a few of them related to Boston Metal, and so I guess this is for ArcelorMittal. So it says, recently ArcelorMittal has invested in Boston Metal. So it means that you are now engaged in both electrolytic technology, high temperature and alkaline, as well as in H2 direct reduction. So does it mean that ArcelorMittal regards all those technologies as complementing each other rather than expecting one to become superior over the others? And which features come to mind that you use complementary roles of the technology in questions, and also related to Boston Metal, how does it come that Siderwin is expected to operate flexibility while Boston Metal says that the technology cannot be operated flexibly? So what is the main difference between the two technologies? So any comment on that?
Thanks, José Ignacio, for the question. Important question. Huh? So, as you know, ArcelorMittal has launched since the beginning of 2021 the so-called XCarb fund. The objective is to support companies which are developing, which are maturing new technology in the domain, in the field of decarbonization. So in different domain, will it be company for energy supply or storage, such as Form Energy for iron air battery, H2 Pro for a new electrolyzer technology, or TerraPower for nuclear techno developer. Will it be technology in the frame of CCU as Lanzatech? And we mentioned the new steel and oil production in Ghent, and also for sure disruptive technology for iron production. And in that frame, yes, ArcelorMittal has funding in the frame of XCarb fund as funding Boston Metal. Our company, ArcelorMittal, bets on both Siderwin and Boston Metal technology to have a major role in the future of electrowinning of iron. Each technology has complementary strengths. There will be a place for both. The footprint of ArcelorMittal and local context are so wide that both solutions will play a role. When I speak about different context, I mean the iron ore availability, the need or not of flexibility, the energy source availability, the integration of this electrowinning process within the mining and or steel making process route. So there is a place for both technologies. So yes, both the Boston Metal and Siderwin processes will fit clearly into ArcelorMittal strategy. It's a very exciting and challenging, ambitious challenge, but for sure a challenge we will earn.
Okay, thank you, Jean-Paul. Let's go for some more technical questions. I think these are mainly related to Daniela. There are a few questions. What types of ores are not suitable for this process?
The ones that have a high amount of contaminants. So the objective is to use as much pure of iron oxides as possible. So we should decrease the amount, the ores that have the lowest content of contaminants.
Okay, there are a couple of more technical questions. How much sodium hydroxide is needed to produce 1 kilogram of iron?
Well, sodium hydroxide is not consumable. So, for example, if we use bulk cathodes, we don't need to change sodium hydroxide. So there is no problem with that. In suspensions, you need to eventually put more feedstock inside. So, but this question should be more related with the people working with the pilot scale. I don't know how much sodium hydroxide they actually use, in fact, but it's not consumable during the tests.
Okay. And is the process tolerant of silica in the feed ore?
Silica will have also some problems for example, when we are depositing iron, the silica can be trapped inside of these dendrites and later can be detached, and because it's soluble in sodium hydroxide, so it will form silicates with sodium silicates. But this, because it was once trapped, it will cause brittle deposits. So we will have weak deposits and we will have much lower efficiency. Of course, yes.
Okay, thank you, Daniela. There are more technical questions. I think that will be for Professor Panías. The first one is, how about starting with extractive processes that reduce the volume of titanium and magnesium? Both metals may be worth to begin it before iron. Professor, you are muted.
The impurities, as I told in my presentation, is the big obstacle we have now in the use of alternative raw materials. So it is reasonable at this moment to try to find a way to improve the quality of these secondary raw materials. And what we are doing now, in most of the cases, especially in the bauxite residue, is to apply hydrometallurgical processes in order to remove some impurities and to make the process more efficient. But keep in your mind that in the case of bauxite residue, the titanium in the form of calcium titanates was the problem. And calcium titanates are not easily managed in the soluble compound. So this is something we are working on at this moment. And this is the correct direction in order to make the bauxite residue a useful alternative raw materials. In some other cases, there are other metals. Magnesium is not a common metal in the case of bauxite residue, does not exist there. But in some other residues, you can find magnesium or other metals like nickel, cobalt, and etc. So the extraction of them before using the alternative raw material will be beneficial. From economic point of view, because we will extract the value of the metals, and also from the energy point of view, because we will make the electrolysis process more efficient.
Okay, another question for you is about the electrical arc furnace dust. Does this material apply?
Yes. Okay, EF dust contains high amount of iron. It is very well known, but unfortunately, iron exists in the form of zinc ferrates. So it seems that this would be a problem for the iron deposition. On the other hand, the presence of zinc is useful because we know very well that zinc has a catalytic role in case of hydrogen evolution. Actually, creates high overpotential and pushes the hydrogen evolution to more negative potentials, making, in this case, the iron deposition more useful. So it has a potential. I never tested this before. It has a potential, but I smell, or I have the feeling, that the achieved current efficiencies will be extremely low, making the electrolysis totally uneconomic. So this is my conclusion, although I never have tested it.
Okay, thank you very much, Professor Panías. So let's move to other questions related to the pilot cell. There is the first one, what's the source of hydrogen bubbles? Do they come from the electrolyte fluid or some impurities in the input material?
Yes.
Yes.
The source of the yes, the source of the hydrogen is the electrolysis of water, and this side reaction can occur on the cathode in the same potential range as the electrolysis of iron oxide.
Okay, another question is, how do you manage to balance the fresh oxide in and reacted oxide out?
As I mentioned during my presentation, we work in a closed loop as so there is no waste of electrolyte, but the concentration of hematite in the electrolyte decrease, and this can have a negative impact on the Faraday efficiency. So that's why we have to feed the electrolyte with the hematite continuously to maintain its concentration in the solution.
Okay, maybe another question for Roland. The flexibility value of Siderwin would be higher in a system dominated by variable renewables?
I guess that is true. If you assume that because of the introduction of more intermittent sources of electricity production, such as solar and wind, that may generate a more volatile electricity price. And if the electricity price is more volatile, more value can be extracted if you have a flexible process. On the other hand, one can also argue that if there is a high flexibility demand in the overall energy system, there will also be more and more flexibility suppliers introduced into the system, such as batteries or other flexible or producers of flexibility, and that may then reduce again the value of flexibility. So I tend to believe more renewable energy sources means more flexibility, means more value for flexible technologies, but it's not a guarantee.
Okay, another question, maybe the last one because we are out of time right now. What are the main drivers for the Scope 3 emissions? That is the main contributors to the Scope 3 emissions.
Yeah, Scope 3 again relates to the overall value chain that Siderwin is part of, and that also includes, and since we've looked at upstream of the Siderwin technology, iron ore extraction and raw materials. For example, iron ore extraction itself is a process that can generate has a CO2 carbon footprint. So again, it is these raw materials that go into the Siderwin technology that can generate still an amount of carbon footprint, and that is then called a Scope 3 emission source.
Okay, thank you very much. So there are more questions, but as we are out of time, we have registered all your questions, and we will generate a document with the answers, and we will send you the link with this document. Also, as I mentioned before, this webinar is being recorded, so maybe probably next week we will send you a link with all this information. So thank you very much to all the partners, to the European Commission for the support of this project, and to all the partners that have been involved in this project. So I would ask all of them to please switch on your cameras so everybody can see you. And this is all the team, a very nice and great team that has been involved in the development of this project. So on behalf of all of them, thank you very much for your interest in this project, and thank you very much for joining in this webinar, and we will see you again and we will be in contact. Goodbye.
Thanks.
Thank you.
Goodbye.
Bye-bye.
Bye-bye.
Goodbye to all of you.